What happens when you need to integrate a rational function? Remember, a rational function is the ratio of two polynomials. Now remember, if the degree of the numerator is bigger than the degree of the denominator, then you have to do long division to simplify that rational expression. But after you've simplified and the degree of the numerator is smaller than the degree of the denominator, and it's still not in any form you can integrate, then we're going to try partial fraction decomposition. The easiest type of decomposition involves just linear factors that are non-repeating. If you've never seen that process, I'm going to send you to a previous pre-calculus video. The second case, which is a little bit harder, you have linear factors, but some are repeating, and you have to take care of that repetition. And again, I'm going to send you back to that video from pre-calculus if you've never seen that type of partial fraction decomposition. The third one is if you have quadratic factors, things that can't be factored like x squared plus 1, and how you take care of that in your setup. And then the last type that fortunately we do not run into very often is if you have quadratic factors that are repeated. And again, you have to take care of that repetition. So if you need to see the examples of how to just decompose the fractions, again, go back to these previous videos. We're going to look at these examples, and I am going to go step by step on how to decompose the fractions, and then of course the idea is to get it into a form that we can indeed integrate. So looking at number 1, our fraction is proper, or a rational function has a smaller degree on top, but it's not in any form that we can integrate. So I look at that denominator and I say, well, how can I factor that denominator? So we can take out a greatest common factor of 2x, and that would leave x squared minus 4. And then of course that can factor further. As the difference of two squares. So I look at each one of those factors. They're linear, they're to the first degree, none of them are repeated. So I can set up this fraction to solve for some constants. So I need to go through and solve for a, b, and c. So there's my equation. I think I said set up a fraction, really setting up an equation to solve for these three constants. So the first thing we need to do is we need to multiply both sides by the original denominator. And of course, if I multiply this side by that denominator, it's going to reduce out, and that is the idea. So I want to get rid of those fractions. Okay, so the two x's would cancel, and I would be left with x plus 2 times x minus 2. Here the x plus 2's would cancel, and I'd be left with 2x times x minus 2. And here the x minus 2's would cancel. So there's our lovely equation. How do we solve for a, b, and c? There are many different methods. But the method I like is to choose convenient values, and I get those from the original denominators, setting those equal to 0. So the first convenient value would be x equals to 0, and then I'm going to use x is equal to negative 2, and then I'm going to use x is equal to positive 2. And that's what's nice about the non-repeated linear values. You get as many convenient values as you do constants. Okay, so what are we going to do? We're going to go to this equation. This is the big one. That's the one we need to use each time. And I'm going to first of all put 0 everywhere there is an x. So I'd have 0 plus 3. And what happens is that anything times 0 here and here goes away, and so we can just solve for a. So we'd have a times 2 times negative 2 is negative 4. So that gives me my first constant. Now I'm going to go through and put in negative 2. Again, going back to this equation, everywhere there is an x, I'm going to put in a negative 2. And hopefully, when you do this a few times, you're going to see that 2 of these are going to go to 0. Okay, so putting in negative 2, so that's going to give me negative 4. So since the negative 2 came from the factor x plus 2, everywhere there is an x plus 2, that is, of course, going to go to 0. And so we have positive 1 equals b times 16. So b is going to be 1/16. So my last thing to solve for is c. And again, going back up here, and I'm going to put in a positive 2 everywhere. So I have 2 plus 3 and again, since that factor came from x minus 2, everywhere there is an x minus 2, that's of course 0. And so I have 5 is equal to c times 16. So c equals 5/16. Now, again, I've done 0 calculus. So we're going to come back up to these 3 fractions. Remember, if I have this integral is now equal to these 3 integrals, I should be able to integrate. And that's what I'm going to do. So here's my original integral with its factor denominator. It's now equal to these 3 integrals. And yes, I know that those constants look weird. I just wanted to tell you that's where you can put them. But of course, we know we can put those outside our integral signs. And so we have negative 3/4 times the integral of 1/2 x to the negative 1, 1/16 times the integral of x plus 2, 1 over x plus 2, and 5/16 times 1 over x minus 2. So yes, I could join those up, so that's going to be negative 3/8. This is just the power rule. Or is it? Why is it not the power rule? Not the power rule, x to the negative 1 or 1 over x. Can't use the power rule. What is that going to be? It's going to be the natural log of the absolute value of x. This is going to be 1/16. In fact, this is going to be also the natural log of the absolute value of x plus 2. We have 5/16 times the natural log of 1 over x minus 2. You will see as we work partial fractions, you get lots of natural logs because you usually end up with your variable in the denominator and just a constant in the numerator. Now, I will warn you that lots of books do some really cool things to join up all those natural logs by using your natural log properties. You don't have to do that for me. Okay, so looking at number 2, again, I have a fraction, a rational function. It's in a proper form. It's not in any form. I can't integrate because if I let this be u, I just don't have the derivative. So I'm going to look at this and say, can I factor the denominator? And yes, I can. This is 2x plus 5 times x plus 1. So again, I have linear factors. That's kind of nice. So I'm going to set up my equation. I'm going to multiply both sides by the original denominator. So that's going to just give me non-fractions. Okay, so what are my convenient values? Again, I let each denominator equal to 0 and solve for x. And that is what I'm going to let x equal to. Again, that's just one method, a method I prefer. So if I let x is equal to -1, I would have 2 times -1. And of course, you're going to see that that is 0. So I have -2 equals 0, and that's b times 3. And then if I let x equal -5/2, that's going to end up 0 because that came from the 2x plus 5. And so here I get -5 equals a, that's going to be -3/2. So if I multiply both sides by 2 over -3, I'm going to get positive 10/3. Okay, so now I have my original problem equals to a, which is 10/3 over 2x plus 5. That's from there. Then plus b, which is -2/3 over x plus 1. So let me write that a little bit neater. I'm going to try. Okay, so now I'm ready to integrate. So remember, the form of 1 over u du is equal to the natural log of the absolute value of u. But I have to have du. So if u is 2x plus 5, then u is 2 dx. So I have to take care of that too. So what's that going to happen? I'm going to have 10/3 because of that constant times 1/2 because of that 2, then the natural log of the absolute value of 2x plus 5. And this one, since the derivative of x plus 1 is just 1, no extra constants are needed. So just a little reducing. And again, I really do want to warn you, Calc Chat and some other people really do a lot of neat things, but not that useful to combine that answer into one big thing. You can, but I would prefer that you just left it like that. Okay, so let's look at number 3. What do we have to notice? We need to notice that that degree is higher than that degree, so we have to use long division first. And so I'm going to divide. That's going to be x cubed plus x squared minus 2x. I need to subtract those. And because long division really mandates descending order, I'm going to put my negative x squared, then my 2x, and then I'm going to bring down the positive 3. So dividing again, I get a -1. So that would give me 3x plus 1. So now I want to take my original integral. It's now in the form of x minus 1 dx plus the integral of 3x plus 1 over this denominator. Then I'm going to go ahead and factor it as x plus 2 times x minus 1. So this is what I need to use my partial fractions with on how to integrate, because I know you can integrate that part. So I had 3x plus 1 over x plus 2 times x minus 1. Again, two non-repeated linear factors. I'm going to have my two convenient values of -2 and +1. So here's my equation. So I'm going to multiply both sides by my original denominator, always my original denominator. So I would be left 3x plus 1 equals a times x minus 1 plus b times x plus 2. If I let x equal to -2, I'm going to get -6 plus 1. That's going to be -3, and of course that's 0. Okay, if I let x equal to 1, should get 4/3. And I want to integrate my original problem, which is right here. So I have to integrate x minus 1 dx plus a, which is 5/3 over x plus 2, plus b over x minus 1. Okay, so this is just your power rule, x squared over 2. That's just your constant rule. Then we have that natural log rule again. And one more time. So you want to make sure you look at the problem first to see if you need to do long division, and ask yourself, do you really need to use partial fractions?